Okay, welcome everybody to our March monthly meeting for Social Techies. Thank you guys for coming. This month, our presenter is Dr. Teresa Escrig. She's an amazing researcher in the field of AI. She worked with Qualitative Modeling. She's run her own startup, worked with automated vehicles. She's worked at Accenture, and she's currently an architect at Microsoft. So without further ado, Teresa, please take it away.
Yes, thank you for the invite. And I want to mention that as we connected like 2 days ago or so, I thought I was going to do a presentation for startups that I prepared a couple of years ago, but I had another one that was more updated. So I'm using one that I'm going to use for another company, but I think it would be more appropriate for this team. And the things that it might be too detailed because it was prepared for another concept, I would just skip it. And it's a good place for us to start conversation. And I also wanted to say that if you have any questions, please stop me at any time because we don't have a tight time, right?
Yeah.
Julian, we can ask questions in the middle.
Yeah.
Having said that, let me.
Sorry.
Can you hear me well?
Yes, indeed.
Perfect. So I titled the presentation, "The Story That Made Us Need Transparent AI." And the agenda that I was including in this presentation is AI at Microsoft Cognitive Services Offering. And that was because I was asked to do that. And it's not that I would normally do it. And that's the part that I might skip really quickly, unless you are interested in knowing. But that's not the topic. I don't want to sell anything here, even to the other company either. It's just to expose what is available. Examples of AI going wrong, and there is where I start being interested in talking about what happened in the field of AI for the last even 5 years or more. Customer learnings in all these years. The responsible AI part at Microsoft Consulting Services, I'm leading that aspect. That's the reason why it's included in the presentation, is because it's basically at the moment my entire focus. How to do transparent AI beyond explainable AI. And then I have a couple of examples. I mentioned that I like to really talk about things that are real and not so much only concepts, that why we need responsible AI and all of that. I think we all know why we need it at this point, but how to do it is what is most important to me. And those two examples are going to the details of how I did it several times already in my career. And then the benefits of transparent AI. Q&A at the end, but some I will skip quickly, and others you can stop me if you need to know more details. This is me. I have a long career in artificial intelligence. I started in academia. I did my PhD in qualitative modeling, which is an aspect of AI different to machine learning, which is what everybody at this point knows as AI, but there is more to AI than only machine learning. And I was the head of a research group, Cognition for Robotics Research was the name. I have more than 100 research papers and books, and I directed also PhDs and got awards. So in academia, I was very successful, but I also felt that I needed to bring what I knew to practice. And there's where I explore other avenues and ended up founding a couple of startups. The first one was Cognitive Robots, and the second one was called Qualitative Artificial Intelligence. When I was in the second startup, Accenture made me an offer, and I became the AI global lead of cognitive computing and computer vision. I thought I could have broader reach with customers and the knowledge that I had if I was supported by a large corporation that already had the customers. That was the intent of me joining Accenture. And then I joined Microsoft as the senior architect. basically working on responsible AI, how to put into practice responsible AI in services, Microsoft services. So I'm the responsible AI champ in Microsoft. So this is the cognitive service APIs and the different aspects that Microsoft has been working on to provide ways, very quickly, easy ways to have AI already incorporated as an API to your system as a startup. There is APIs for language, speech, the cognitive services lab that also contains the text to speech and search. Then there is vision as well, face, emotion, video indexer, search, all related with Bing search and visual search, and then decisions like anomaly detector or personalized. So those are the set of APIs that are included in cognitive services. They are organized in these 5 buckets: vision, speech, language, knowledge, and search. And they are all dealing mainly with machine learning algorithms as well. It's easy, it's flexible, it's tested. That's the way we present it to our customers, but I really don't want to go into any of these here with this group. I want to focus on why we need responsible AI. So we have been using in everyday actions that we do AI even without knowing it. In our phone is completely filled with AI algorithms. The pace of innovation is really fast, and the way those algorithms influence us is hidden, is really not out in the open. How the search engine, for instance, works and how can influence our decisions is really hidden. We don't know how Facebook is showing out as the post that we do. If we have a business that is based in Facebook, we really don't have any control. What movie is really recommended to us is that not that relevant or death or life threat, but it might influence also our way of thinking. Everything influences our way of thinking. And I think that this is one of the most challenging areas at the moment, that we don't know how much we are influenced by the AI that surrounded us. So and also we have observed that there are in many places AI goes wrong, and there has been many studies that shows up that fact. I like this slide or this part to the upper right. That is a study from the Cornell University that we're taking stop signs and studying how the ML algorithm, it was a deep learning algorithm, when there is shades, shadows on top of the stop sign, or if we add some stickers or the pixels are removed or changed, the stop sign is being interpreted as 45 speed limit. In these 2 first cases with 100% of accuracy, and in this one with 67% accuracy. So it's really high in all cases. And if we think that we use deep learning algorithms to identify signs in the road for autonomous vehicle, this is a really dangerous situation because we cannot really trust or we know how to hack a system. What is happening in autonomous vehicles is that they are using other ways to ensure that we identify a stop sign that is not only computer vision, but that's because computer vision is not working properly. So they use like GPS signal, and they find that the car is at an intersection and we should expect a stop sign and not a 45 speed limit. But we have to add extra layers of data because this one doesn't work well. Other examples is this deep learning algorithm for object detection. They overlaid an algorithm to define what pixels were used to identify objects, and the red pixels are the ones that are used to identify the boats, which doesn't correspond to the boat per se. So the pixels used to identify the object is not related with the object, but with the reflection of the boat on the water. So that's also show us what pixels are being used to really identify objects and how easy it could be hacked. Another example that was a study at Google, they used, they trained a machine learning algorithm to identify dogs. And when they input these jellyfish as into the system, the result of that interpretation of the jellyfish was also dogs. So if you train a machine learning model to identify dogs, it's going to see dogs everywhere, also when there's no dogs. That's an example for AI going wrong with computer vision, and this is another example of AI going wrong with text. That was the type bot that Microsoft launched in 2016. It was, and in 24 hours it transformed itself from loving people to hating people. It's because that's what they say, it was hacked with teenagers that were trying to teach the bot hate speech, and it took it. Microsoft put that down immediately, and this was the beginning of the process of getting responsible AI within Microsoft, and end up by hiring me also to put it into practice. But that started in 2016 with this problem. Then we passed into customer learnings from years of deploying machine learning models into customer sites. And I took out the statistics here because I didn't have data to back it up. It was more of an informal conversation with data scientists within Microsoft. But basically, 80% of the POCs, proof of concepts, that Microsoft is doing with customers are not deployed into production. 80%. That means that the customers don't have a return of investment, so there is no value, that is not useful for customers, and Microsoft doesn't have anything in return either. From a POC that is not deployed, we don't get Azure consumption, which is the way that we measure success. So success for Microsoft is also success for customers. If it is not useful, it's not used, then nobody gets benefit from it. And 80% of the engagements that we do with our customers is really high. So why is that happening? And that customer learning is why. There is poor data quality, so the outcome is not good enough, and I have examples of when that happened. There is a lack of transparency on how the models work, or failing to understand the business. I like this a lot, even not necessarily because of the title, but because of the example. It was in predictive maintenance for a large equipment manufacturing firm, and in this case was part of the 20% of ML models POCs deployed into production. It was working really well until the system defined that one of the big machinery had to change the oil 6 years prior to what the experts expected the oil to be changed. And then everybody was asking why the system is giving me this that is not really what I expect, is not intuitive, the answer. And the next day, the answer was completely different. So instead of 6 years now, prior, and now you need to change the oil like 4 years. So it was a very unstable way to predict when the maintenance has to happen without a why, without a context. So immediately it didn't work. So something that was deployed into production and useful became not useful because of the lack of transparency at the end. Another example is data used to train a model is not representative enough, and it's not that we don't know when it's going to be representative, it's that sometimes what the customers think that is going to be representative and what we need is different, and there is no enough conversation to know. So it becomes something that is not working because we didn't ask the right questions, believe it or not. Another situation that happens with POCs not going into production is that it was never intended to go into production. They just want to say they're using AI, so only for publicity reasons, or they want to test the waters, or they want to see if that problem could be solved using ML or things like that. The model output is not good enough is also a problem, and the model not integrated into the production because it's too expensive is another one. And this is a very key component. If you develop a model and you don't know how you're going to integrate it into the rest of the production pipeline, then it's also not useful. It's not used, and therefore it doesn't get any benefit for anybody. And these are the customer learnings of the other side. So when the 20% of POCs that work, why they work. There is good quality data, is relevant, right granularity, shape, frequency is high quality. It has clear outcomes that are agreed with the customer. We use MLOps, ML operationalization in those cases because the non-standard way to solve ML doesn't work. It doesn't go beyond POCs, proof of concepts, ever. So MLOps is a must to really be successful with ML. Visualizing ML performance is also really important. And this is where the responsible AI part comes into play, how we are going to visualize that performance if we don't have data, if it is a black box. So including things that are relevant to someone, how the model behaves is very important. And then how we do the knowledge transfer to the customer, because if we solve the problem, but they don't know what to do afterwards, then it's not going to be successful either. So those are the customer learnings for the cases that did work. And why we need transparent AI. So these are also, over the years, I evolved this slide in many ways, depending on also the audience that I have in front of me. In fact, the other deck that I was going to use today had this one in a much less evolution, and that's why I came to this deck, is because I wanted to talk about these type of things I think is relevant for this group. The first thing is that we need to trust the technology, and the executives are really worried that the AI that is black box is not trustworthy. And so it's 72% of 6,000 plus executives said that they could not trust black boxes. Trust is really important, not only for executives. They are, at the end of the day, they're responsible to deploy machine learning models, or in case of that you sell machine learning models to customers, but also the end users, how they can trust the technology unless we are forcing them to use that technology, as it happens with the search engines that we don't know and we use it anyway. But being critical is also part of the equation in what is happening. So trust and being critical and not trust when it's not trustworthy is what we need to do. Then there is a bunch of regulations, outside regulations, like for everybody is GDPR, you probably know, General Data Protection Regulation that started in Europe in 2018, where people have the right to have the explanation, the logic behind ML model given to them, and also the right to opt out of the AI decision process altogether, and even retrieve the data so it's not being used to train any ML model. All of that is in the GDPR. How companies are complying with the GDPR is another story, but that's what it contains. So I was very glad to see this happening, because that's a way to force the opening of the black box situation and not continuing developing ML black box without any railway protection. And the other one is the California Consumer Privacy Act. So everybody in California has the right to opt out of any personal information of in any corporation or any set of data to be used to train any model. Then we have the quality assurance. So when the algorithms are black box, it's very difficult to define quality assurance, and that's really evident in the autonomous vehicle industry, which is the industry that with most advanced use of AI. That's the one that contains inside the autonomous car the most amount of AI altogether. And when an accident happened with the car, then there is no way to know what caused the accident. So what they do is they normally go with another car with the same model trained, with the same type of data to try to reproduce the accident. And they might reproduce the accident by the car going into or starting the same error, and then the person that controls it stop it before it happens again. But still, they know they can reproduce the error because it happens again with another car, but they cannot go to any line of code to know what happened with that error. So quality assurance is really a nightmare. And the whole industry at the time where the accidents happened, I haven't followed that industry so closely in the last year and a half or so. But before that, the whole industry stopped and they had to go into quality assurance mode, and they didn't know how to check the algorithms. They, for sure, don't know how to give the information of what happened to the regulation groups that exist, and it's really a problem, which is related with the other one, time and cost of algorithm development. In that industry particularly, we had cars on the road saying that they're autonomous for a long time, and also defining that the level 5 autonomy will happen in 2020, 2021. They had very strong deadlines for that, and the time came and they had to back up out of that commitment because the technology was just not ready. And my assumption on all of this is that it will never be ready unless we add something else that I will include here in the presentation. And another big problem that happened is that there is a slow AI adoption, and that's very clear. That's very clear also at Microsoft. There is a high churn of ML adoption in general, and the companies have a high expectation, but there is an unclear return of investment, and it has been a huge amount of investment in many resources, as we know. That's why ML has been out in the market for so long, and it has a big wins. It's because there has been a large investment, but then the return of investment is really low, is questionable, and in my point of view, we have the danger to go into another AI winter if we continue this way.
Teresa, can I ask you a question about, you said that the most advanced usage of AI was in autonomous vehicles. Can you talk a little bit more about kind of what kind of AI is used in autonomous vehicles?
Yeah, it's a combination of different usage. So deep learning algorithm for computer vision. I have, in fact, an architecture in the slides, in the deck, that explains what type of technology is included in autonomous cars, because that is one of the examples I'm going to go into.
Oh, awesome.
So
Okay,
if
cool.
it's okay, yeah, I will explain even with details. But yeah, there is a lot of AI included in the autonomous vehicle.
Okay.
Let me do it there with the architecture.
Okay, awesome. Thanks.
This is another slide that I like. Thank you. This is another slide that I like a lot to talk about because it summarizes what the challenges that I was mentioning before. In MIT Technology Review, people were saying that we can build these models, but we don't know how they work. And I like this one that is really old, from 1934, but is really current. Prediction from observation cannot verify, it can only be falsified. And that's what happened with the statistical models of ML. So we predict from history, from the data that has already happened, and never can be verified. It only can be falsified in the sense of we only can have accidents in the car. We cannot ensure that the algorithm is correct in any formal way, in any mathematical, formal, theoretical way. So it is never tested enough. We can have percentage of reliability. So and that's how the lawyers work. If this technology works 96% of the time well, then I approve it as a lawyer. But what happened with the rest 3-4% of the times that we don't know, because we don't know how that works. Are you going to put your kids in the car where you have a 3% of chances that might not work and you don't know when? But machine learning algorithms are a theoretical art, not a science. And the art word here is important. And AI will bring serious risk unless you approach artificial intelligence as a strategic imperative, meaning the business owners have to be involved with the decision making of what to deploy in production and what are the risks and versus benefits of ML algorithms in production in their company. These are the responsible AI principles that Microsoft has defined over the years, and these are the ones that I'm putting into practice in Microsoft Consulting Services. But Microsoft is putting this into practice in all orgs. So all the products at Microsoft will have to be compliant with these responsible AI principles when they are completely implemented. It's not the case now, but that's the direction that Microsoft is going. Fairness, reliability. I'm not going to go into the details of what that means because I think everybody in the group will understand. Privacy and security, inclusion, transparency, and accountability. Of course, the four first are really important, but transparency for me is key, and I will go into the details more in this deck. And then accountability means that everything that we develop, we are accountable for developing, and that's huge. Everything is everything, even if we just don't use it, only developing, and then the customer uses it, and they may change even the usage of things like that along the way. But we are accountable for what we do and what is the impact in individuals and in society of that technology that we develop. And that's really critical. So all of them are important, but the last two are really making a commitment. Microsoft has also developed tooling. Some of them are open source, like InterpretML and FairLearn are open source tooling to define, to do explanation and to define fairness, identify fairness, and also mitigate fairness. And all of that is open source. And then to protect, I'm not so familiar with this tooling. And then the control part with MLOps is also really critical. I mentioned that before. So the combination of MLOps and Interpret ML and Fair Learn is what I'm working at the moment. And here's another one that I don't explain when I'm at Microsoft. So this is the work that I did at Accenture prior to joining Microsoft. And I explain in the example of autonomous vehicles, the difference between having an AI/ML only. And in fact, as we will see in that architecture that I promised is going to show up, it's a combination of ML models within the autonomous car. It's a pile of them. So you have AI/ML without any explanation or transparency. The car works well most of the time, but when there is an accident, you don't know where to go. I mentioned that already, that quality control is very difficult. And there is no way to explain why it works and things like that. Also, never know when the technology is mature enough to deploy completely and be trustworthy. So there's a problem when we have black box alone. The next step up is to have explainable AI. And this example was done by NVIDIA, also with autonomous vehicles, and they overlay an algorithm to define the pixels used by a deep learning algorithm that was an end-to-end solution. So meaning the input was all the sensors, including the camera, the images from the camera, but also LiDAR and sonar, all the sensors that the car had. And that was a deep learning algorithm being the outcome, three or four control of the car. So steering the wheel, accelerating and braking. Those were the three components output. I was thinking if there was any other one, but I think it was only three. And the overlay algorithm to detect the pixels that were used in that process of deep learning algorithm, so that the pixels that are relevant for this particular use case are the ones that we humans will also consider as relevant for this particular task, which is the corners of the road, the corners of the cars in the road, the line in the middle of the road. So all of the pixels that were showing up were relevant to the task. So with that explainability, which is this type of explainability is what Microsoft has also developed for computer vision. There is where we are at. This is the point. Still, there is no relationship between the context of the car and the decision made by the car. So if something happens here, or these cars, for instance, these cars that are detected as relevant pixels for the autonomous car to consider, still there is no relationship. I don't know why my autonomous car is telling me to turn because I'm seeing the cars this way. There is no correlation in explainable AI. And that's happening with every explainable AI that is in the market. So this is the most advanced that I know of example of explainable AI on computer vision. And the ones with text and things like that go in that direction as well. And again, as I said, this is the limit of Microsoft. And if we go to the next step, transparent AI goes beyond this. This is the work that I did at Accenture, and this is the one that I will show you with the architecture later. This is the interface, taking the time. Are we going to finish at 12 or?
Yeah, this is planned to kind of go on to about 12.
Okay, I think I need to speed up then. So in the autonomous vehicle is the blue arrow here. the rest of the cars are around the autonomous vehicle in different colors and also directions. So what we did was integrating several qualitative models to define when the cars around the autonomous vehicle would be a problem or a risk for the autonomous vehicle. Like it would be in red if this car behind the autonomous vehicle is too close, or in yellow if there is a potential risk in the future, like this car might come to our lane because it's slightly turning. So the context of why the autonomous vehicle is making the decision is defined with the other cars around the autonomous vehicle, and that's stored. So we can go back and know when that error happened. So the context is completely recorded, so the errors can be reproduced, and that's the next step of Transparent AI app. And to do Transparent AI, I'm going to go a little faster, so I guess we have still 5 minutes to chat. Is the integration of knowledge representation and reasoning, which is an area of AI that has been active, the same as ML, for over 60 years, is the integration of knowledge representation and reasoning with ML. That's how we got Transparent AI, which is beyond explainable AI. And this is the first example. So we did DNA sequencing out of a chip. The chip is this, represented with this, that contain 30,000 nanopores, and this is the representation of one of those 30,000 that are in a centimeter square chip. And then they grew up some polymer on top of the nanopore to make it the nanopore even smaller, because through that nanopore we are going to drop the DNA string. And there is an enzyme that cuts each one of the DNA molecules as the string passes through the nanopore. It cuts it. And then there is a wire that that crosses the nanopore. It leaves the nanopore door open, but there is a current that crosses, an electric current that crosses the nanopore head. And that current is what is measured. So when the DNA string passes the nanopore and the enzyme cuts each one of the molecules, the electric signal is cut, and the size and shape of that cut is what defines a time series signal. I know I said many things there, but I hope everybody's so excited.
Yeah. Can I interrupt to ask a question?
Mm-hmm.
Okay. What is the qualitative model, and how does it give us context for the autonomous vehicle?
Yeah, it's the next slide.
Okay, awesome.
Next slide. So this was the definition of the problem. So they didn't have any software. They tried to develop machine learning twice and failed because the time series signal wasn't stable, and they were able to do 30% accuracy of manual classification, meaning naked eye. So they had the signal come in, and it was a plot of the signal, and with the naked eye they could classify the 4 bases with 30% accuracy, but they couldn't have a software to do it automatically. And there is where we came in play and solve the problem using qualitative modeling. So this is the first example of doing qualitative modeling and how we could do it in a transparent way. So yeah, it took a long time to get there here, but this is the example. So this is the technology behind it. We apply qualitative modeling for time series signal. So we get something like a plot, the time series signal, and each one of the peaks that go down corresponds to a DNA base. the top is electric noise, and we cut it off. So we only consider the bottom peaks. And for that, we had the qualitative model had 3 angles. So time series signal goes from left to right. So the only angles that can happen in that signal is A, B, and C. It could happen other in between, and we consider others in between. But at the end of the day, these 3 were enough to define the base. So we reduce it to 3 at the end. So angles is the first qualitative feature that we identify in the time series signal. And the second one is the relative length of the segments. So if we extract this DNA base peak here outside, we have a peak that is composed of segments, and as the absolute length is not a way to measure, because that was one of the problems with the unstable signal that they got, is that depending on how they were putting the wire in the chip, or other things that were not controllable by them, the amplitude of the peak was varying. So we could not use absolute distance. We had to use relative length. And how do you do relative length? You compare.
I'm sorry. I'm really sorry. Is this in relation to cars? It's not, is it?
No, no,
It's
no,
about
no. This
DNA.
is DNA sequencing. I have 2 examples. One is
Okay.
DNA sequencing, and the second one is cars.
And the problem we're trying to solve with DNA sequencing using this is what? I'm really sorry.
Yeah. No, that's fine. There was a startup that created a chip to do DNA sequencing, and the way they did the chip is what I explained in the previous slide. And they had unstable data, so they tried to use ML models twice and failed with that unstable data. And with qualitative modeling, we solved the problem. So this is the explanation of how the problem was solved. That also I wrote a patent, and it was issued, and I sold it to Accenture as well. So it's part of their story. Sorry if I didn't give the context, so you couldn't follow me.
So the properties that are relevant to DNA sequencing are like the length segments of the DNA and angles. DNA sequences have angles?
No. So the way to solve this sequencing with this particular chip, as it has the wire, the electric wire, and the DNA is dropped in between the electric wire, the outcome of that chip is a time series signal. And each one of the peaks correspond to the DNA base that passes through the nanopore.
Okay.
So it's basically, this signal is the output, because the way to solve the sequencing with that nanopore technology works this way. Any other technology could work or some other way. In fact, we have DNA sequencing that works with tinctures. That's the current one in the market. It's not this one. So this is like a more advanced way of sequencing. This will be real-time sequencing if we solve the problem.
Okay.
Makes sense now?
I think so. Thank you.
So basically, this is for DNA sequencing because they were doing DNA sequencing this way, and we got a time series analysis. But in fact, this way to solve the problem applies to any time series signal. It could be heartbeat, or it could be voice. Anything that is a time series signal, we can use the same type of qualitative modeling. So I'm going to continue because I don't see faces. That's the problem with me facing only my my deck. I don't see any face and reaction. So unless you ask the question, I don't know if you understand or follow me or anything. So my apologies for that. It's better when we do it in person, for sure.
So is the qualitative modeling is mostly around, it sounds like the qualitative modeling stuff is mostly around measuring or analyzing the way that the actual time series data moves over time and extracting out some sort of information from that.
So this is the beginning. The next slide continues. So this is the main features of a time series signal: angles and relative length segments. In order to define that a segment is medium size, you compare that segment number one, which is the first one here, with the rest of the segments and define, is this one larger or smaller than 2, than 3, than 4, than 5? So you're comparing. And you say, oh, 1 is bigger than 2, smaller than 3, equal to 4, bigger than 5, and smaller than 6. Then you count the number of bigger and smaller, and if they are the same, as this is the case, then we have a medium segment.
Okay, so like the segment in the graph.
Exactly.
Okay.
The segment number 1 is medium compared to the segments in this peak, not an absolute measurement. There is no numbers here.
Oh, okay. Very cool. Very different.
There is no number. So that's why it's qualitative. It's not quantitative. We don't have any angle number. We don't have any length per se. We are just comparing.
Oh, wow. Okay. That's very cool.
Yes, exactly. So now you have the representation of the peak this way. So you have segment number 1 is angle A, so it's down, and medium segment medium length. Segment number 2 is C, so it's up, and small. So you're representing qualitatively the segments in a peak.
Oh, wow. Okay, cool. I've never seen this before. This is very cool.
Yeah, so let me continue. If we have this is the representation, which is the first step, and it's really interesting because you have the essence of the information. You don't have the real measurement. And why is this relevant? Is because that's the reason why ML didn't work, because from one time to another that they run the same experiment, the distance, the number of points for a particular base or the amplitude of the signal was completely different. So they couldn't measure anything. That's why it failed. But qualitatively is the same peak, the same shape. So with that you can define shapes.
Wow. Okay.
In a way that is independent on the number, on the measurement. But what happens when you want to classify? Because we are classifying 4 bases. Is a sequencing of DNA. We have 4 bases in DNA. So you're comparing bases, which are comparing peaks. So how do you compare peaks? Qualitatively, you don't have any number. So you have the representation. So 1 is down and medium, and so on, of the 2 peaks. We have the complete representation of the 2 peaks. So you are now comparing 2 things. You are comparing angles and you are comparing lengths, relative lengths. And you have the distance. If from not knowing the angle to not knowing the angle is zero, the distance from A to A is 0. So zeros in here when there is the same. And when you're comparing A to B, the distance is 1. And when you're comparing A to C, the distance is 2. 2 meaning 1 step or 2 steps. So it's a way to measure the difference. It's very different or is not that different. That's qualitative comparing angles, and also qualitative, I pass to the next one, and qualitative comparing relative distances. And in this way, you are going to be able to measure how different they are. So what we are doing here is basically starting from the top and top, comparing and adding how much different they are, and starting from the bottom and the bottom, because sometimes we don't have the same number of peaks, the same number of segments, and then it's difficult to compare one-to-one. But we can do it anyway, qualitatively. So we'll get a number out of this comparison, and then we will know if it belongs to the same bucket, which is the same base, or not. We are able to classify doing that. No numbers, and we had only one file of data that was not even complete to be able to pass it through our system, through our AI system, and we got 84% accuracy of DNA classification.
Oh my God.
Sorry, just a question. And thank you. This is very interesting. You also apply any denoising algorithm? Sorry for the background noise. When you have to deal with the time series, even in the qualitative with using qualitative model.
I didn't follow the word that you said. Can you repeat it?
Do you use any denoising algorithm?
Oh yeah. I didn't mention that, but we cut the top of the signal completely, not the bottom. So we apply the denoise of the signal to the top. It was I don't remember exactly now the algorithm name, but it's very typical to really denoise the signal. And the bottom will also contain noise because the electric signal contains noise. But we didn't want to clean up the bottom so much, just in case we lost in the process some parts that were relevant. So we denoise it afterwards qualitatively. Like if we had two segments that were going down, like in cutting the middle, then we were adding it as one and things like that. So we were denoising it in other ways, but the top was completely cut. So yes, you're right.
Thank you.
I'm already on time, over time, and I didn't talk about the autonomous vehicle stuff, but I promise that I will show you the architecture and is here. So the perception part is a deep learning algorithm. The prediction part is another one. So this is going to predict where is the location of the car around us in the next milliseconds, and also the autonomous car. Routing is, as the name says, where we need to go with the goal that we have. HD map contains the points that define the segments of the lane, which is defined with polygons, which was very, very weird. Localization is where we are at, and then the control is where the car is really making the planning makes the decisions and the control executes the decision that is run through the physical canvas of the car. So there are many areas. Each one of them contains ML algorithms. And that's the Baidu Apollo architecture, the open source architecture. And what we did was changing planning and translating the numbers, quantitative numbers that we were getting from the rest. This is in the middle of the process. It's not perception, which is the beginning of the process. It's in the middle of the process. So we translate it into qualitative terms, and then we made the decision based on those qualitative terms. So those were the two parts that contain planning. And with that, we were able to open up completely and have the context. So go to the next level of transparency. So it's not that we avoid all ML algorithms, we add or interchange something in this case to get that transparency. And this is a little example of all the models that were included in there and the outcome. The outcome I already explained it to you. And the benefits is that is intuitive, the decision is repeatable, and all stakeholders understand it. All stakeholders, end users, business owners, lawmakers, even the insurance companies. It accelerates the development because we now know how to code an algorithm. It's not a black box that we really don't know how it works. Qualitative modeling is code in a regular way of coding, so you know what line of code you're running as well. And it increases trust because it's transparent. You see how it works and the context. So that's it. I know I rushed at the end. I hope that it made sense to all of you, and I'm going back to see your faces.
None of our videos are on, but thank you very much for this presentation, Teresa.
Mine's on.
Oh, yours is on? There you go. Thank you very much for this presentation.
That was very complex. That was very nice.
I hope you follow also the line of thought. I know it's in an hour to go over many things that are complex and are research that take years, but I thought the DNA sequencing with time series is simple enough to understand the concept of qualitative modeling. So I hope I made it clear enough.
Yeah, I got a lot of new understanding from qualitative modeling. I had never seen it before, so I thought this was super cool. Yeah, so thank you for the presentation, Teresa. Thank you all for coming. Michelangelo, Amanda, Jason, Hal, Jonathan, Alex, Ben, and Christina. Does anyone have any questions for Teresa? No? Okay, I'm going to end the recording here. And hopefully this actually gets recorded and works this time.